So Big Idea 6 still focuses on equilibrium. In the first part of the Big Idea 6 video, we focused on general equilibrium and solubility product, calculating Q, the reaction quotient, K, the equilibrium constant, etc. In part 2, we're going to focus on how equilibrium, a specific type of equilibrium associated with acids and bases, and buffers and titrations, and using Kas and Kbs and Kws and pH. And we're going to get to that right after one small part I forgot to mention in part 1 of the relationship between thermodynamics, ideally delta G, and K, equilibrium constant. There's an equation on your equation sheet that tells us if we know the free energy of a reaction, delta G naught, we know it's going to be equal to negative RT ln K, where R is a gas constant of 8.31 joules per mole Kelvin. So this is the relationship between these two values, and what we can see, just a refresher, because of this negative sign, if delta G is a negative number, let's say negative 100, and we know that R and T are constants, essentially we have negative natural log of K, which is going to make K a positive number. So as we can see, we're still having the proof that if delta G naught is less than 0, we have a spontaneous reaction, and K is greater than 1. And on the other hand, if we have delta G greater than 0, or K is less than 1, that is a non-spontaneous reaction. So just a quick review on those conditions. We also need to be able to manipulate reactions that are not at equilibrium, where this is the value of Q. We got to predict how will delta G change in order if the reaction shifts towards equilibrium. And we'll work on problems associated with that in class as well. But the focus on acids and bases starts with definitions of acids and bases. So the first definition that we learned was the Arrhenius definition. So the Arrhenius definition of an acid is a molecule that makes H+. So an example is HCl. When it's dissociated into water, it makes H+ and Cl-. So this would be a Arrhenius acid because it forms hydrogen ions. An Arrhenius base, on the other hand, is a substance when dissolved in water makes hydroxides, OH-. So an example of that is NaOH. When it dissociates, it makes a sodium ion and the hydroxide ion, OH-. Because of the presence of that hydroxide, we would say that this is an Arrhenius base. So this is the Arrhenius definition that you need to know. Acids make H+, bases make OH-. We also need to know the Bronsted-Lowry definition, which we're more familiar with. Bronsted-Lowry. Okay. And a Bronsted-Lowry acid donates H+, whereas a base accepts or gains hydrogen ions, H+. So for example, if we had, a reaction like any generic HA plus H2O forms H3O plus and A-, which of these is the acid and base according to the Bronsted-Lowry definition? Well, which compound donated a hydrogen? Well, HA became A-, so it lost a hydrogen, so we would say this is the acid, according to the Bronsted-Lowry definition. H2O, on the other hand, started with 2 hydrogens and ended up with 3, so this molecule gained an H, so we would say this is the base. The other two vocab terms we need to know are conjugate acid and conjugate base. Well, when the acid loses its proton, whatever is left over is called the conjugate base. Okay? And when a base gains a proton, the resulting compound, in this case H3O+, is called the conjugate acid. Okay? So essentially the conjugate acid is just a base that's gained a proton, and a conjugate base is an acid that's lost a proton. So we need to be familiar with those two definitions. If we want to start quantifying acidity and basicity, we have to use the pH scale. So just a quick refresher, remember P mathematically means negative log. So the pH, if we're calculating the pH, it's the negative log of the concentration of H plus ions. That P holds true for anything we want to calculate. If we want to calculate the pKa of a substance, it's the negative log of the Ka value. If we want to calculate pKb, it's the negative log of the Kb value. And if we want to calculate pOH, it's the negative log of, hopefully you got this by now, hydroxide concentrations. We need to know how to manipulate and use these four equations frequently. We also need to know how they're related. And hopefully you remember that pH plus pOH is always equal to 14. So whenever you add up the pH and the pOH values of a substance, you should get the value of 14. Let's say you're at pH of 7, which is a neutral pH. What is going on there? Well, the concentration of acid, H+, and base, hydroxide, is equal. If they are equal, we are at pH 7. Let's say you have more than one than the other. Let's say you have more hydrogen ions than OHs. Well, then the pH is going to be less than 7, and you're going to be acidic. And if, on the other hand, you have less hydrogen ions than hydroxides, the pH is going to be greater than 7, and the solution would be basic, a basic pH. So these four equations up here, and understanding this relationship, you should be able to interchange between any of these values with relative ease, quickness, and comfort. We can define acids and bases as either weak or strong, depending on how they dissociate. So a weak acid only partially dissociates, okay, which is different than a strong acid or base. Okay, so this means that only some of the molecules ionize. Okay, so if you have HA, not all of it is going to completely turn into H plus and A minus. It's actually going to be in an equilibrium, where some H plus and A minus is being produced, but we also have some of the weak acid still present. So let's say, for example, here we have acetic acid, okay, HC2H3O2, and its equilibrium. We know the Ka value can be looked up in a given table. So let's say we had this solution, and we knew that the concentration was 0.20 molar. What is the pH of this weak acid? Okay. Well, in order to do this, we need to essentially just set up an ice table, because we need to figure out what is the concentration of hydrogen at equilibrium, because we know that pH is negative log of H+. So if we can figure out the concentration of H+, we can figure out the pH value. So what this would look like, well, we're starting with 0.20 molar of acetic acid. We have no H+ to start and no acetate ion. So this is kind of our ice table here. As it dissociates, that's going to become negative, positive X, positive X. So we're essentially going to get 0.20 minus X, X, X. Since we know the Ka value, we can set that up equal to these relationships. 1.8 times 10 to the negative 5 is equal to X times X over 0.20 minus X. Just to make that a little clearer here. Now, we could use the quadratic equation. We might have to do some tricky algebra, but remember, we can assume that for weak acids, the change is so small because they dissociate so little. These Ka values are so much less than 1 that this change in X is going to be very, very small relative to the initial concentration. It's going to be so small that essentially it doesn't matter. So essentially we're left with 1.8 times 10 to the negative 5 equals X squared over 0.2. So you should go ahead and do the algebra to check yourself. But if you do the work, X is going to be equal to 1.9 times 10 to the negative 3. Now, what does that give us? That gives us the concentration of H+, of acetate ion, and we could figure out the equilibrium concentration of the acid. But that's not what the problem is asking for. It's asking for the pH. So we need to do the negative essentially log of X, because that's the concentration of H+. Boom. Boom. Plug that value in. Again, you should be able to check this yourself to figure out what it is to build your confidence, and you get a pH of about 2.7, which supports the fact that this is an acid. pH is less than 7. On the other hand, strong acids and bases are different because they completely dissociate. Every single molecule of a strong acid or a base, HA, is going to break apart and dissociate into a hydrogen ion and the conjugate base. Every single molecule. Therefore, there's no equilibrium. Okay? There's no Ka value necessarily. Okay? So instead, if we were given a compound like HCl, and it has a 0.20, let's use a different concentration. Let's say it has a concentration of 0.01 molar. We know that since there's a 1-to-1 ratio of hydrogen to chlorine, that means we're also going to have 0.01 molar H+. So if we wanted to calculate the pH of this, it would just be pH is equal to the negative log of 0.01, which is equal to 2. No Kas, no ice tables needed, but that only works for strong acids and strong bases. So how do we know what are strong acids and strong bases? Well, this is one time where you got to memorize some things. Strong acids, there's 6 of them you got to know. HCl, hydrochloric. HBr, hydrobromic. HI, hydroiodic. HNO3, nitric acid. H2SO4, sulfuric. And HClO4. These 6 you must have memorized. What about the strong bases? Remember, group 1 hydroxides and heavy group 2 hydroxides. So lithium hydroxide, sodium hydroxide, potassium hydroxide, and heavy group 2, which is strontium and barium. These are strong bases that will completely dissociate into Li and OH, for example, so then we could calculate the POH, and then from there you could calculate the pH, etc., etc., etc. There's one special condition we need to know, and that's for water, because water is in equilibrium constantly by dissociating into H plus and OH minus. If we were to write the equilibrium expression for this, since water is a liquid, and these would be aqueous, the equilibrium expression would be Kw equals concentration of H plus times the concentration of OH minus over nothing, because this is a pure substance, so we don't care about it. This, at 25 degrees Celsius, is a constant. Kw, called the auto-ionization of water, is equal to 1.0 times 10 to the negative 14th, always at 25 degrees. So if you think about that, that's equal to H plus times OH minus. And since these concentrations are going to be equal, essentially these are kind of both like X. We have like X squared equals this value. X, which is equal to the concentration of H plus and OH minus, is 1 times 10 to the negative 7. Okay. If we're at neutral pH and we're at 25 degrees Celsius. So you just got to remember Kw is equal to this value, which is also given on the equation sheet. The last relationship that's special about Kw, since this takes into account acid and base concentration, we can also kind of take into account Ka and Kb values. So in fact, Kw is always equal to the Ka times the Kb of a compound. So if you know the Ka of an acid, HA, it dissociates into H plus and A minus. And if you also know, Kw, so you can always figure out what Kb is, what the base dissociation constant is for the conjugate base. Because you can plug this value in here, you could plug in the Ka here, and just solve for Kb. So manipulating between Ka, Kw, and Kb is something that we should be able to do as well. What about when we mix acids and bases together? Well, when we do that, we have reactions called neutralizations, because some of the acid or some of the base is getting neutralized by the other compound. So first we're going to talk about neutralization reactions where we have a strong acid or base in excess. So for example, 35.0 milliliters of 1.5 molar HCN with this Ka is mixed with 25 mils of 2.5 molar KOH. Calculate the final pH. Well, first we got to figure out what is present at equilibrium, because in order to get pH, we have to know the concentration of H+. We don't know that right now because some of the H+ here is going to get neutralized by the KOH. So to do that, we got to figure out how many moles of each do we have. Okay. Well, using this value, I have 35.0 milliliters. 1,000 milliliters is 1 liter. I have 1.5 moles per 1 liter. So the number of moles of HCN is 0.052. If I do the same math but with the KOH, I'm going to get that I have, you can check me, 0.062 moles of KOH. So now these are going to react. They're going to cancel each other out because one of them is going to be the limiting reactant. One of them is going to be also in excess. Well, what's the reaction going on here? We have HCN plus KOH is going to produce CN plus and H2O. Since K is essentially a spectator ion, it doesn't really matter. So we kind of have OH minus and CN plus here. Right? So just set up an ice table. Okay? We have 0.052, we have 0.062, 0. This is our unknown. We don't care about it because it's a liquid. So which is going to react? Which do we have less of? Okay? Well, we have less of the HCN. So all of this is going to get used up. So the 0.052 moles of the HCN are going to react with the 0.062 moles of hydroxide, leaving 0.01 moles of OH minus. Okay? Well, to figure out the concentration, we have to divide that by the volume, because molarity is moles per liter. Well, we have 35 plus 25, which is 60 milliliters. Convert that to liters, move the decimal over 3 times, so 0.06 liters. So the molarity is 0.17 molar of OH minus. So now from here, I want you to be able to figure out what the pH is. Okay. So go ahead and try to figure out what the pH is. Pause the video, and then come back in a second to finish it. Well, you know POH is negative log of OH. So if you do negative log of 0.17, you'll get 0.76. And then we know that pH plus POH is equal to 14. So the pH is going to be 14 minus 0.76, which will give you 13.24. So this was a neutralization reaction where we had excess of a strong acid or base. In this case, it was excess KOH. And we knew that, just check yourself, because we had more moles of KOH than the weak base, the weak acid. If the relationship was not 1-to-1, then you'd have to take that into account. But for now, we're going to move on and talk about the Henderson-Hasselbalch equation. The Henderson-Hasselbalch equation. Henderson-Hasselbalch equation, okay, is used when we have weak acids or bases in excess and with buffers, which we'll talk about in a second. And there's two forms of the Henderson-Hasselbalch equation. pH is equal to pKa plus log of A minus concentration over HA, where this is the conjugate base, essentially, the weak acid that's dissociated, and this is the concentration of the weak acid. We could also write it as POH is equal to pKb plus log of the conjugate acid of a base over the base. Either one of these two forms. We are much more familiar with using this one. This is the one I'm anticipating would be used much more frequently than the one below, but we should be able to manipulate either one. So, how do we use the Henderson-Hasselbalch? Let's say we have a reaction like this. 60 mils of 0.5 molar C5H5N with this Kb is mixed with 25 milliliters of 1.0 molar HCl. Calculate the final pH. Well, let's see, what do we have? We have 60 mils, well, 1,000 mils is 1 liter, 0.5 moles per 1 liter. So how many moles of that compound do I have? That's going to come out to 0.03 moles of C5H5N. I can do the same thing to figure out the moles of HCl, and if I do that, I find out I have 0.025 moles of HCl. So what compound do I have in excess? I have the C5H5N. My weak base is in excess. Okay? So if they react in a 1-to-1 ratio, all of this strong acid is going to get used up, and I'm going to be left with the difference, 0.03 minus 0.025, so 0.005 moles of C5H5N is in excess. Okay? So again, I want to figure out what is the concentration of this. So I got to divide it by the total volume, in this case 85 milliliters, so 0.085 liters. If I do that, I get a concentration of 0.29 molar. Okay? That's the concentration of this compound. All right? Well, how much, when this acid reacted with this base, how many moles of this conjugate acid did I make? Well, since all of it reacted, I'm also going to have 0.025 moles of HC5H5N plus over 0.085 liters. So the concentration of this value is going to be 0.29 molar. And I apologize earlier, this was a mistake. This math didn't come out to 0.029. This should have been 0.059 molar. So now with these two quantities, I can just plug them into the Henderson-Hasselbalch equation because I know how much of acid and conjugate base that I have. So we know that POH is equal to PKB plus log of the HC5H5N over C5H5N. So if I just plug in all my values, it's negative log of 1.5 times 10 to the negative 9 plus log of 0.29 over 0.059. And if I do the math for this, the pH value comes out to be 9.5. So therefore the pH is 14 minus that, which gives me a value of 4.5. Boom. Which makes sense. I had excess of this. The pH does not change as frequently because there's a weak base present. And what is that? Is called a buffer. A buffer resists change in pH. Okay? And the way it works is you have a weak acid and its conjugate base present. So an example is like right here. Okay? 0.2 molar of acetic acid and 0.5 molar of sodium acetate are mixed. If the Ka is this value, what is the pH? Okay? Well, this is super simple. It's a buffer. I know that because I have a weak acid. The reason I know that is because it's not one of the 6 strong acids. And I have its conjugate base. Okay? The salt version, sodium acetate. Ooh, so that should be my indication. Boom, buzz. I have a weak acid and its conjugate base. This is a buffer. It's not going to change pH very much, and I can use Henderson-Hasselbalch. So I can just plug in my values. pH is equal to pKa, because I'm given the Ka, plus log of the conjugate base over the weak acid, the concentration of both. So if I go ahead and plug those values in, okay, I'm going to get pH equals negative log of 1.8 plus log of A minus 0.50 over 0.20. If I do the math and figure it out, I'm going to get a pH is equal to 5.1. Super simple. The way I recognize this buffer is I had to have a weak acid present and its conjugate base present. That should indicate buffer, Henderson-Hasselbalch, buffer, Henderson-Hasselbalch to determine the pH. There's two other words that we should be familiar with. One is a polyprotic acid, and this is a compound that has multiple H pluses. Think about the prefix poly, so something like H3PO4 can dissociate into H plus and H2PO4 minus. Since this still has two hydrogens, that could dissociate even further into 2H plus HPO4 2 minus, and it has another H plus that could even dissociate further. So you got to be able to recognize polyprotic acids by looking at them. The last one is an amphoteric molecule. What is an amphoteric molecule? Amphoteric molecules can behave in two different ways, so as acids or bases. Best example is H2O. H2O can dissociate to form H plus or OH minus. It can form both ions, so we would say it is amphoteric. An example from before would be H2PO4. It could either lose a hydrogen and act as a base, or it could gain a hydrogen to become H3PO4. It can go both ways. It is an amphoteric molecule. The last thing that we learned how to do with acids and bases in equilibrium was titrations, and we did a couple lab with titrations. Remember where we had, our beaker with our burette up above, and we were dropping in an acid or a base, and we were measuring the pH and seeing how it changed over time. There's a couple different titrations we did. One was a strong acid with a strong base. And when we do a titration curve for a strong acid or a strong base, the curve will always look the same. Okay? It'll be a general curve like this, where the line is very, very steep. Okay? The pH changes very, very suddenly because there's no buffering capacity when you have strong acids and strong bases. This point right in the middle here has a special name. It will be at a pH of 7 if you're mixing a strong acid with a strong base, and this is called the equivalence point. So you need to be able to recognize that on a titration curve. And the equivalence point is special because when the moles of acid are equal to the moles of base. Moles of acid equal moles of base. This is true at the equivalence, any equivalence point, okay? But since if we're mixing a strong acid and a strong base together, that's going to occur at a pH of 7. So you got to be able to recognize axes for a titration curve, pH always on the y-axis. The volume of base in this case is on the x-axis, which must have meant that in our beaker we had an acid to start. You could also do it the other way around, where you had a base in here and you added acid instead. Either way, same type of curve. If you're titrating a weak acid with a strong base, okay, the curve is not going to look the same. The curve is going to be more gradual to start, and then it's going to shoot up. Okay, where this slope, let's make this a little more clear, is going to be just ever so slightly upwards. And that's because this region, since we have a weak acid, this is the buffering region. The pH is not changing very much. Okay, and there's a special name for the point right here, halfway through the buffering region, and it's called the half equivalence point. And what you have to remember about the half equivalence point is that's where the pH is equal to the pKa. So if you know the pH by going over to the y-axis, you can figure out the pKa value, and then if you know the pKa value, you can figure out the Ka value for the acid that you're titrating, just based solely on the titration curve. Remember, that is the half equivalence point, so the volume here, let's say it was 20 milliliters that you added. That means you've added half of the base needed to get to the equivalence point, which would be at the same place, up here. So this would be at 40 milliliters of base added. Okay. This is the equivalence point. Since you're titrating a weak acid with a strong base, this equivalence point is going to be greater than 7 pH. pH of 7 would be somewhere around here. It's going to depend what it will be exactly on the concentration of the acid and the base and the Ka value. But what you need to recognize, if you see a titration curve with a gradual line, that's a buffering region, which means we can figure out what the half equivalence point is and what the equivalence point is, the volume added. Okay. If you know the pH equals pKa, the last thing you got to recognize is, oh, if pH is equal to pKa, I remember that Henderson-Hasselbalch equation, where log of A minus is over HA. If these are equal, they cancel out. So to make log of this value 0, these have to be equal also. So the concentration of A minus is equal to the concentration of HA when you're at the half equivalence point. Okay? Titrations of weak acids and strong bases. Very last type of curves that we need to be able to recognize are polyprotic titrations. And the way we know these is because they have multiple hydrogens that can be neutralized. So we would have a curve that essentially has two half equivalence points. Okay, a buffering region right here, a buffering region right here, where this is essentially pKa1 is equal to the pH at this point. And up here, pKa2 is equal to the pH at this point. The equivalence points are also still right here, so remember, whatever volume this is, let's say this was 10, since that's the half equivalence point, this volume would be 20. If this was 40, that would be up here at 80. So recognizing polyprotic curves is the last thing we need to know about acids and bases, and you are done.